Okay, welcome to part 2 of 5 for the Unit 3 population notes. In part 2, we're going to look at survivorship curves, carrying capacity, and then population growth and resources availability. All three of these are very tightly wound together. So when we talk about survivorship curves, this is just a graph that shows survival rates for a group of individuals of the same age in a population. So you're looking at the rate of survival from birth until you get to the maximum age of that species. So we'll look at we'll look at an example, but they're broken into type 1, type 2, and type 3 curves, and we'll relate these curves to K and R selected species as well. So this is what a survivorship curve looks like. So you can see that on the x-axis, we're looking at the percentage of maximum life expectancy. So these would be, it's not years, but it could be years. Because we put 3 different species on the same graph, we're just looking at their percentage of maximum lifetime expectancy. For instance, humans, that might be 90 years, whereas a bird, that might be 5 years. So these aren't the same these aren't always the same when we're talking about what years are down here, so don't think of that. And then the number of individuals living, this is also kind of looking at a percent, and it's also on a log scale because that drop off is a little bit different, and same thing with the birds. But you can kind of get an idea that a type 1 species off of this graph, survivorship is pretty high from birth pretty much until mid to late end of your life. The survivorship, the odds of a human or a type 1 species surviving is very good until you reach the end of lifetime expectancy. Type 2, one example is birds. There's really just a continual linear kind of regression where their expectancy or their ability to survive just keeps going down. All this means is that many of their species from birth will survive. As they get older, their likelihood of survival goes down. The last type is type 3. An example here is trees. A type 3 graph, you see a very quick drop in life expectancy for the percentage of the individuals. What this means is not all individuals, and actually the majority of individuals of a type 3 do not make it very long. But once you get a species that has made it a pretty good span, 25% of the maximum, their likelihood of survival is now very good. So while there might be, say 1,000 trees that start from seedlings and sprout, after about 25% of the expectancy, most of those, like 90% of those species, will have not made it. But the ones that have made it to that point are very likely to continue to making it to live to the maximum expectancy. When we talk about K species, a K selected species is usually going to fall in the type 1 and type 2 range, and then your R selected species are usually type 3. So you can imagine that insects, for instance, maybe have a very high infant mortality rate. They don't survive very long, but the ones that make it through those very early years or days will survive longer because of the competition has dropped. Their likelihood of survival goes up. Carrying capacity hopefully isn't a new thing for most of us, but basically carrying capacity is when the resources no longer support growth of the population. We usually think of carrying capacity as K, so that's how it would usually be denoted. When we overshoot the K or the carrying capacity, it means that the population has exceeded the resources available, and you start seeing resource depletion. So, this is one of the graphs where that capacity, so you see on the bottom left, the carrying capacity is shown by a line. The problem with this is it's not completely accurate because when we get this overshoot, we're going to be using more resources than are available, and therefore you're going to start to see a decline in the resources available, which will eventually cause the carrying capacity to fall. So this graph really shows that overshooting where the population exceeds its carrying capacity. The population is allowed to continue to rise just a little bit, and once it gets to a certain point, that would be the maximum overshoot. They're using so many resources that the actual carrying capacity has become degraded, which is going to cause the population to decline in a very rapid manner. So it's really important that we understand that when we exceed our carrying capacity, we are changing our carrying capacity, and different species are doing the same thing. If, for instance, the carrying capacity of if the carrying capacity is denoted for a specific fish species as available oxygen, when we get to this overshoot period, because there are so many extra fish, the amount of oxygen that was originally available is going to drop, and that is going to cause the carrying capacity to start to decline. It's also going to cause, because of the higher populations, more death, which will cause more more nutrients to be introduced, which will cause more algae growth, which can cause less oxygen, even less oxygen available. And so there are a lot of factors that kind of come into play where when we reach this overshoot, we end up getting a degraded carrying capacity. When we talk about the impact of a carrying capacity on an ecosystem, the biggest thing is that when we get that overshoot, you usually will see a severe or even catastrophic decline of population. And that's because the problems that occur when you exceed your carrying capacity cause more and more competition, which can lead to famine, disease, or conflict. One of the good examples is an exponential growth and overshoot of a population of reindeer. And this is something that really happened, that we're able to see, and you get to see that the carrying capacity was far overshot. And as soon as that population overshot the carrying capacity, there was this very quick decline and crash of a population, where the population actually died off so quickly and rapidly that it scared a lot of people. A lot of the scientists that were looking at it weren't sure what was happening until they were able to understand that they had overshot their carrying capacity by such a large amount that, yeah, you're going to see a bottleneck effect of the species. And then as far as population growth goes, population growth is very reliant on the resource availability. We got a chance to see this with our little modeling activity when we went outside and we played a little oh deer. The available resources are the most important thing that affect a population's size. And so what's important to understand that over any scale of time, be it years, decades, eras, all resources are limited and they are finite. There's no such thing as an infinite number of resources. So there will always be a carrying capacity for any species. There will always be a point at which a population will overuse its available resources. The difference between different species is how does that species respond to the overshoot, and how do the resources respond to an overshoot. If the resources respond in a downward shift after an overshoot, then the population is going to die off. If there is a lower population growth and the resources are not depleted as quickly, then there is more of a chance of a stabilization at a carrying capacity where a species can survive without a dramatic or catastrophic population decline. We're looking at two types of resources, abundant versus limited. If there are an abundant amount of resources, the population is going to increase. If there is a limited amount of resources, then there is going to be a decline in population. So when resources shrink, the potential for unequal distribution of resources will result in increased mortality, decreased fertility, or both. This will always cause a population to decline either to or below the carrying capacity, and it depends on how catastrophic the response is that this will happen. This is an example of a negative feedback loop wherein you will have, as you use up your resources and a population grows, the feedback is going to be that the carrying capacity will be reached, and so the population has to fall. Sometimes it falls all the way. Sometimes it falls a little bit, but because the resources are replenished, it starts to rise again and then fall again, and then there's this equilibrium that eventually could be reached in theory. So this is a simplified diagram. We saw this before, but this is just to kind of remind you. As a human population, for instance, surpasses the carrying capacity, we're going to have an overshoot. Because of that overshoot, we're going to be using more resources than are available, which means we will have a depletion of our natural capital. If you don't believe that we're going to use more resources than are available, remember back to when we did the how many Earths would we need if everyone lived like you. As we use up those resources, the natural capital is going to decline, which is going to create a degraded carrying capacity, which will in turn cause the population to crash. Many population scientists are trying to find out at what point is the human population going to reach its carrying capacity, and what will the response be. So that'll end part 2. Make sure to like and subscribe, of course, and check out part 3, which is up next.